So the next reaction type to cover is gas-forming reactions. And gas-forming reactions are really aqueous double replacement reactions from which you get a gas that's formed. Okay, so to be really clear, not every reaction that forms a gas is an aqueous double replacement reaction. So not every reaction that forms a gas is considered a gas-forming reaction. So based on that classification, though, there are certain products we look for in gas-forming reactions, and I've listed them down here, but we'll go over them in a little bit more detail. So what I want to do is give you, so those are the products that we look for to identify gas-forming reactions, but I want to give you a quick view of what some of these reactions look like. So some reactions, the gas is formed directly from the double replacement or the ion exchange. So that's what we're referring to. So H2SO4 and lithium sulfide react together, and we get an exchange of the ions. So the lithium and the hydrogen double replace each other. You get lithium sulfate and H2S, and H2S is a gas that's formed directly from the reaction. And the other way that we get gases from the reaction is that if you get decomposition of the product. So, for example, if you take HCl and sodium bicarbonate, and you react them together, you get sodium chloride and carbonic acid. Now, carbonic acid is relatively unstable, and what it ends up doing is decomposing to form H2O and CO2 gas. And so that's how we get the gas in some of the gas-forming reactions. If you look at how this works, if you take and you draw a line under here and you add these reactions together, all the reactants will be on the reactant side, all the products will be on the product side. You'll notice that there'll be H2CO3 as both a reactant and a product, and you can just cancel those out. And what you'll end up with in the place of carbonic acid, you'll end up with H2O and CO2 gas. So that would be rewritten as HCl, I'll leave the states out, NaHCO3 reacting to form NaCl plus H2O plus CO2, and this is the gas of the gas-forming reaction. So here's a more complete list of the reactions. It's actually a complete list of the reactions that are considered gas-forming reactions. So when hydrogen sulfide or dihydrogen sulfide are formed from a reaction, then what that means is a gas is evolved because H2S is a gas. But anytime that you form carbonic acid, sulfurous acid, or ammonium hydroxide, these always decompose into a gas, which the gases are listed here: CO2, SO2, and NH3. A simple way to remember what the gas is that is formed is to look at H2CO3 and recognize that when CO2 is formed, water is also formed as part of the process. So CO2 is actually known as the anhydride of carbonic acid. It's what carbonic acid is without a water molecule. And so all of these are more or less anhydrides of the compounds listed on the left. So if you look at H2SO3 and you take H2O out of it, you'll notice that formula equals H2SO3. And the same thing with NH4OH. What you do is you think about this plus H2O. Those two together make up the formula NH4OH. So the products from carbonic acid, sulfurous acid, and ammonium hydroxide are always water, and then the anhydride, the compound that is formed without the water. Okay, so some example reactions where you might see these things happening. Here's a hydrochloric acid and potassium carbonate through a double replacement reaction. Again, the potassium replaced by the hydrogen and vice versa. You get H2CO3, and then the H2CO3 breaks up to give you H2O and CO2. So that's similar to what we were talking about here. We have H2CO3, but this time it's made from bicarbonate. The bicarbonate then breaks apart to make H2O and CO2 to give you this overall reaction where we see the carbon dioxide gas. So the same thing's happening here. HCl potassium carbonate makes H2CO3, which then breaks apart to H2O and CO2. For HCl and potassium sulfite, then we have the same kind of thing taking place in the double replacement, that is the swapping of the ions. You get H2SO3 that breaks up to water and its anhydride SO2. And again, with ammonium chloride and potassium hydroxide, you get ammonium hydroxide in the double replacement reaction, which breaks apart to give you H2O and NH3. So what I'm going to do is walk you through how you would go ahead and do this for a reaction of magnesium carbonate and hydrochloric acid. And then we'll go ahead, because you need to know how to write both the molecular and the total ionic and net ionic equations. So those are the ionic equations that I'm referring to up there, the net total ionic and net ionic equations. So to begin with, we have magnesium carbonate and hydrochloric acid, and from nomenclature rules or from the periodic table as well, you know that magnesium has a 2+ charge. Carbonate, we're going to use our T43, or we're going to memorize it some other way, but you'll have CO3 2-. And then hydrochloric acid comes from chloride, so it's HCl. So those are my reactants. And so I could think of HCl as being H+ and Cl-. And so I'm going to get carbonate and hydrogen forming a compound, right? And I'm going to get magnesium and chloride forming another compound. So that I'm going to have MgCO3 plus, I have to do the states here, plus HCl, which will be aqueous, making, and then my products will be H+ and CO3 2-, so I need two positives, H2CO3, and then MgCl2. Now I'm going to need to look up some other states in here, but when you see this, you should automatically think H2O and CO2 gas, like that. Okay, and H2O will be a liquid. So that's an automatic when you see carbonic acid, that you break it apart. Now magnesium chloride will be aqueous. But for magnesium carbonate, if you really want to know whether or not what its state is, you really need to take a look at the solubility rules. And here are the solubility rules that we looked at before, right? And this is the compounds. This is the page 2. This is page 2 of 2, right, of the solubility rules. Carbonates are generally insoluble. The exceptions are all soluble, but if you look at these, you don't see magnesium on here, which means magnesium carbonate is a solid. So now I can fill in that state as S. And chlorides are generally soluble, so I knew that one already, so I went ahead and put that one in there. I knew magnesium wasn't an exception to that. So now I have my molecular equation. That is, we're crossing this out, and we're sticking with H2O and CO2 gas. Now the next thing to do is to split up everything that's either ionic and aqueous or soluble, and the strong acids. And so what I can do is I can write MgCO3. That doesn't change because it's not ionic, aqueous, or a strong acid, but HCl is on the strong acids list Oh, sorry, I forgot to balance this, by the way. That's the balancing of it. And so I get 2H plus Cl minus, 2 Cl minuses. That makes H2O liquid plus CO2 gas plus magnesium 2 plus 2 Cl minus. And then I'm going to underline the squiggly line, which I always use for aqueous rather than trying to write aqueous over and over again. And now I get to cross out the spectator ions. So this equation, though, is my total or complete ionic equation. So total or complete. Now, my spectator ions are the ones that don't change, and so I notice that, for example, magnesium is with the carbonate here, and it's separated over here, so that's not a spectator ion. The CO3 actually became part of the CO2, so that changed. That's not a spectator ion. The H pluses became part of the water, so that's not a spectator ion. But the chlorides are here, and the chloride is over here, so those are spectator ions. So now what I can do is cross out my spectator ions like this. And now I can write my net ionic equation, and that's everything but the spectators. So I'll rewrite for my net ionic. I'll rewrite everything but the spectator ions. And again, when you're writing these, what you really are writing is the stuff in the reaction that actually changed and underwent a chemical reaction. The spectator ions themselves are not actually changing, so they really are not part of the reaction. And again, I have these aqueous ions that I'll underline, and that's my net ionic equation.